live in 20 seconds.
Great, thanks.
Good morning, everyone. A very warm welcome to the second Saturday lecture series. As you all know, we have an interaction every second Saturday of the month, and this has been going on for many years now. And we have had a great response from all the students and teachers from all over Pune. But this year we've got this special chance because of most of our interactions being online. We've got a special chance to take this event to all the students across India. And so therefore we have a chance to interact with the same person who gave a great talk at IUCAA in the Chandrasekhar auditorium, and then have an additional interaction. So in this series, we at the Inter-University Center for Astronomy and Astrophysics bring to you practicing scientists who have had a lot of work done in science or science education, etc. And they present to you their work in very simple words, and they are free to speak to you and probably answer your questions related to science, related to careers, and how you yourself could contribute to their own research field. So we are lucky to have today here Professor Somak Raychaudhury, who also happens to be the director of IUCAA and a great supporter of all our education and outreach programs. He's a very friendly scientist, and you can see his lectures. So many talks and simple discussions that he's doing throughout this pandemic. So we respect that, and thank you, Professor, for being here for this special interaction today. This is not a second Saturday, it's a fourth Saturday, but well, the more the better. So,
no, it's like thanks. Thanks are open or closed every other Saturday. They call it second Saturday.
That's right. Yeah. So in the same spirit, we will therefore now welcome Professor Raychaudhury, who has given his lovely talk on our place in space. So maybe I would request the professor to give us a basic briefing about what the talk, what you wanted to say through the talk, and then we'll find the answers, find the questions on the YouTube chat. You're all welcome to put your questions in the chat next to your video, and we'll get them answered in this live interaction. Professor.
Great, thanks. Good morning, and thank you very much, Samir. And welcome to everybody who has turned up on a good Saturday morning. This talk, so our second Saturday program has been going on for a long time, and normally in our Chandrasekhar auditorium, we have 500 people, and we fill that auditorium because we have a limit on the number of people who can come from the schools and along with their teachers. And then they come, and there are other activities that go on. And normally, when we are having this in person, we have an English talk like this one. And then it's followed by a Hindi or Marathi version of the same talk. And on this particular occasion in 2016, when I gave this talk, this was just after I'd come back from being away from IUCAA for a long time. And so we're given this talk, and then Samir gave the Marathi version of this talk just after that, again to a full auditorium. So at that time, close to 800 students heard this talk in both languages. So it is quite interesting to go back to this 5 years later, almost 4.5 years later. And what we are looking at, I mean, not much has changed because this was a very basic talk about the talks. The whole idea was to orient people who haven't really thought about astronomy in the biggest sense as to where we are in the universe. So so part of the talk was very elementary, and part of the talk was related to my own work. So it is very contemporary. And the idea is that the universe is made up of galaxies. And this is something that we did not even know 100 years ago. So when Einstein was publishing his theory of relativity, he did not know that we live in a galaxy, right? This is in the 1930s or so. We learned that we live in a galaxy. And there are the basic building blocks of the universe are galaxies. And just like molecules are the basic building blocks of matter. Now, so I talked about in this talk, and I hope everybody here has listened to the talk. The link was given in the poster. And I talked about the history of how we came to know about these galaxies. As early as the 18th century, people like William Herschel and Charles Messier were looking at the sky and looking at stars, and looking at some stars are fuzzy and some stars are point-like, and then trying to figure out what they are. And then in the 20th century, Hubble took up this idea of obtaining spectra of these objects. And spectra tell you a lot more about an object in the sky than just a camera picture, an image. And not only does the spectrum give you information about the chemical composition of that object, and so it tells you what it is, but also because when a source is moving, the spectral lines in the spectrum also move. They are red shifted or blue shifted according to whether something's going away from us or coming towards us. He was able to establish that all these fuzzy objects in the sky, the nebulous objects in the sky, which people didn't know whether they were different from stars or not, most of them are at a very high distance, and they're all moving away from us in velocity. And thus, he made a distinction between things that are stars or products of stars and things that are actually very, very far away, but consist of 10 to the power 10, 10 to the power 11 stars. And these are called galaxies. And that we live in one of them. So I talked about the Milky Way, our galaxy, and how the universe is expanding. And we came to understand the expansion of the universe. But the interesting bit that I talked about, this of course a lot of people know, and a lot of people are aware. There are many other talks. Then I talked about my own work in here, which is to do with where we are in this whole picture. So we talked about our galaxy's neighborhood, which is a local group, and that it is near a bigger cluster called the Virgo cluster. The universe is full of clusters of galaxies and groups of galaxies. And that over the last 20, 25 years, we have discovered that we are actually moving in the universe with respect to the rest frame of the universe, which is the cosmic microwave background. And the question was, why are we moving with respect to the universe, even with respect to the expanding universe? So if the universe is expanding, we are somewhere, but on that expanding universe, we are also moving. And this question was asked in the early 90s, late 80s, around the time that I was doing my PhD, and I got involved in this work. And I talked about how we found out, and there were people who had suggested that maybe we are being pulled by something called the Great Attractor. But then eventually, by doing a lot of work, we found out that there are these big collections of matter around us called superclusters, which are clusters and clusters. At that time, we hadn't discovered what is known as the Saraswati supercluster, which also, if you remember, a few years ago, this was done in IUCAA. But at that time, we were working on it, but we had already found out some of the other big superclusters, the Shapley supercluster, which I discovered 30 years ago as part of my PhD, the Pisces supercluster, and things like that. And it turns out that these big conglomerations of matter, of dark matter and galaxies, they are pulling our galaxy through the rest frame, which is defined by the expanding universe. So I talked about how people found that and things like that. So not only did we talk about our place in space with respect to the other galaxies, but we talked about also our motion in space with respect to the other galaxies. So that was the gist of the talk. Now let's see whether people have seen this talk and have questions about it. I'm very happy to answer questions. Back to you, Somak.
Sure. So, a lovely brief introduction to the talk. We do have some questions coming in, and but I'll just also refer to a lovely film that is there which was made on these scales of the universe. So that you could travel through these scales. So this was called Powers of 10. And way back in the, I think in the 60s or 70s, this was made by Charles Eames. So the students here, they could go online on YouTube and look for Powers of 10. There's also another interesting clip based on the same thing called the Cosmic Voyage. So look for these. These are very exciting things, and you can actually see lovely animations, animated picturizations of whatever the professor said. And these are based on real data, not the galaxies and the distribution of the clusters, galaxies in the clusters. You can see based on real data. So yes, yes,
to say something about this. The Powers of 10 has a very interesting story that I think a lot of people will be interested in. When the Powers of 10 was made in the 1970s, of course, the digital technology was not available, and Google Maps were not available.
Yes.
But and so actually, what it does, it starts from somebody lying in the park in Chicago, on the banks of the lake, and it takes the picture from the hand, and in powers of 10, which is 10 times the frames increase, and it goes wide angle and shows the whole park, then the whole lake, then the whole state, then the whole country, and the earth, and then goes on all the way to the universe and comes back. Now this has been done, the one you talked about, the Cosmic Voyage, and there are some others, by employees of Google using Google Maps and Google Earth and Google Sky. And they've been doing the same thing in a very nice, they start from Seattle where Google headquarters is and things like that. But the interesting thing about that 1970s Charles and Ray Eames, the husband-wife couple who used to make these short films, was that even though they made the film was made by an astronomer called Philip Morrison, who's a very famous professor of physics at MIT. And he was spending a sabbatical year at the National Institute of Design in Ahmedabad at that time.
Oh, wow.
He's a physicist. He was designing things for teaching. And it was the National Institute of Design people who actually helped him make that film.
Amazing. Oh.
So there's a very interesting connection with India in that film. And I've heard Philip Morrison, he's now dead. I've heard Philip Morrison talk about that experience of how he made this set of slides first called Powers of 10, which used to be shown on a slideshow. Then Charles and Ray Eames saw Charlie and Ray Eames saw that and said, let's make a movie out of it. But the original set of pictures were actually done during a sabbatical in India, which was very interesting. Anyway, go ahead.
Wow, what a connection. What a connection. Thank you for letting us know.
Yeah.
We'll put links to these clips on YouTube in the chat eventually. Now let's move to the questions. Yes, we have some questions coming in, and an interesting question about you've answered you've covered a lot of ground about where we are in space, but then there is also a lot of material that is invisible in the universe. So the question is, why is most of the universe invisible?
Right. So that's a very, very interesting question, and that's what in astronomy is all about. And one of the reasons astrophysics is a very new subject, even though people have access to the stars, it's not like atomic physics. You really needed the equipment to go into the atom and look at the atom, and so that technology had to wait till the 20th century. The skies are just there, right? And people can just see the sky. And that's why astronomy is also the oldest science, because you didn't need any equipment to see the sky, and people are very interested in the sky. In those days when there was no television or newspapers or radio or whatever, very early on, the only thing you could see in which things happened and it was entertaining was the sky. So comets came, you had eclipses, you had phases of the moon, you had all kinds of things happening. And so people were quite interested in, and so there was this notion that that's what the universe is. That is the stars. And so if we find the edge of the stars, we'll find the edge of the universe. Then with telescopes coming, we figured that, and that's from Galileo's time, and then we figured that there is much more than what the sky sees. But even then, when we look through the telescope, we are actually looking at what the eye sees, and which is normal light. In fact, the electromagnetic spectrum has much more than the normal light. And people used, for example, radio waves to study the universe from the 1930s onwards, because then you had to build the radio antenna, radio technology, all that came in the 20th century. And then people realized that if you look at a radio telescope and look at the same things, they look very different, because you're seeing very different things. You're looking at the cold gas in a galaxy, or you're looking at the magnetic fields on the effect of the magnetic fields, the particles going on magnetic fields on the surface of a star or near a black hole. And those things, you don't see the normal radiation that you see with the eye. And then, and this is why astronomy is a new subject, in the 1960s and 1970s, after we went to space, we started putting telescopes on satellites and taking them to space. And then we realized that we can study the universe in X-rays and gamma rays and ultraviolet and infrared. All these are stopped by the atmosphere. They don't come to the Earth. And then we got some kind of a mosaic picture of the whole universe. I use the analogy of the famous the story of the elephant being studied by 7 blind men, and then the famous poem that you often read in school of the 7 blind men who were trying to touch an elephant and trying to see whether what the shape of the elephant is, and one caught hold of the tail and said, "Oh, the elephant is just like a rope." And one caught hold of the ear and said, "Oh, the elephant is like a fan." And then one caught hold of the leg and thought the elephant is like a pillar. But only when they started talking to each other, then they realized the elephant is all of these things, right? And you have to, so from the optical and the infrared and the radio and ultraviolet, you get different views of each object. And then you have to put them together to make a story. And this is what astronomers have been doing in the last 50 years or so, I think. And this is why it becomes the newest science, because all these technologies, all these different kinds of, all these different ways of looking at, perceiving the universe. And they started telling us a different story about all these things. So then we figured out that when you look at a galaxy and we see a picture of a galaxy, we see only the stars. And even when we look at it in the infrared, in the radio, in the ultraviolet, we see different parts of the galaxy. But there is, just by looking at their motion, we figure out there is much more in the galaxy that is making them move in a way that only the things that we see will not be able to. Because on those scales, the only dominant force is gravitation. And so if you look at, for example, the neutral hydrogen, the atomic hydrogen that you see in radio waves, and you can find how fast it's moving in spiral galaxies, and it turns out it's very far out from the center of the galaxy, still moving very fast. And if you calculate how much matter is needed to make them move that fast, you find out that you need about 10 times the amount of matter as compared to what you see in just the light, if you assume that they come from normal stars. So things like that led us to the concept of dark matter. And so we now know that there is quite a lot of kind of things that we don't see. For example, we see only the stars. But you want other kinds of telescopes to detect the cold gas, the hot gas in X-rays, cold gas in radio, the dust in infrared, the young stars and the most massive stars, which also emit mostly ultraviolet. They don't emit much. Very interesting, the most massive stars don't emit much light, which we can see with our eyes. You need ultraviolet. And all that, even if you count all that, then there is on top of that much more matter. And so the universe is full of dark matter, but it's also full of matter that emits only in other parts of the spectrum. And then there are black holes which don't emit any light at all, but you can feel their gravitation through gravitational waves, right? So we are just learning about this dark part of the universe. And in fact, I gave another second Saturday lecture, I think it was a couple of years ago, called The Dark Universe, which we might go back to at one point, where we talked about, not today's topic, but talked about the dark parts of the universe. And so you can look through the archives of our YouTube. I think that talk should be there too, no? It was, I think, in 2018.
Sure. Sure. Yes.
Yes.
Do look for other talks. I can see there are several questions. Some of them are also not related, but I understand that you want to ask astrophysics questions to the professor. So there are a lot of questions that can be answered by other talks which are there in the playlist series. So this interaction is actually also to draw attention to the to all the other talks which are there, not just second Saturday, but there are also public lectures which are given by very senior scientists, which you could also have a listen to, and you'll find answers to your questions in there. Now, coming back to this interaction, we have some relevant questions to the topic. One is about we're talking about our place in space. So we are in the Milky Way galaxy. So one question is that we are kind of at the edge of the galaxy, or maybe almost to the edge of the Milky Way. But what would happen if our solar system was closer to the center of our Milky Way? It's a hypothetical question, but maybe interesting.
I'm going to share a slide from. Can I share a slide? Is there a? I can, no? Just check whether I'm allowed to share a slide.
Yes, you are.
Yeah. So from the original talk. So I've got the original talk here, and if I take that and we're discussing this talk that I gave in 2016. So here is a picture of our galaxy, and I showed this slide in that talk. So you can see that the Milky Way on the right-hand side is the face-on view. You can look from the top, and that's where you see. And here's where, if you can see my cursor, here is the sun with the Earth on this side, right? And it's actually halfway to the edge. It's as you can see, 8 kiloparsecs, which is about 25,000 light years from the center of our galaxy, right? So here, now, it's a very, very interesting question that you have asked, because if you look at how our sky, what does our sky look like? Our sky is just full of stars. And this is because all the stars that we see with the naked eye in our sky comes from the fact that we are here around this Earth, and we're looking at the sky in this direction. And it depends on where you are on the Earth, the latitude. If you are in the southern hemisphere, you are looking in this direction mostly. And if you're in the northern hemisphere, you're looking mostly in that direction outwards, right? That's the orientation of the Earth. And this is why, for example, as you go towards the southern hemisphere, you see more and more of the center of the Milky Way. You see the Milky Way like this. This is from Chile. And you can see that here's the center of our galaxy. And here is the plane of our galaxy, which is covered with dust. And so you're looking towards that side, right? So this is Chile up in the sky, and in the night, right? And so you can see this is a real picture. This is an artist's picture. Okay. So but then from the northern hemisphere, mostly we look at. So it's not just a question of what would happen if the sun was somewhere else. Think of where you are on the Earth. The sky changes. Very interesting question. So if you look at here, you're seeing this really thin layer of stars. This thin layer here. And you're looking through that screen of stars, and so all the stars in the sky are like that, are in that screen, and the Earth turns, and so from different parts of the year we're looking at kind of slightly different parts of the sky, of that screen, right? So, for example, certain constellations and certain things are seen in different parts of the year, and not visible because the Earth is turning. But in general, that's what we see. Now, your question is, what would happen if the sun was here? Or maybe the sun was there? So both are interesting things to ponder. If, for example, the sun, as you asked, was much closer to the center of our galaxy, then you can see that the disk becomes thicker in the middle. And then we go into the bulge of the galaxy. So the general number of stars in the sky would have been much, 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 much more. And in fact, you would find that in the night, the amount of light that you would have is so much more, you wouldn't know about darkness at all, right? So here in Chile, because the Milky Way is up there, on any given night, even without the moon, you can read a book. Just the light of the Milky Way. Now imagine being closer to this, right? And closer, such that instead of 25,000 light years, you are 2,000 light years away or 3,000 light years away. Then you are just totally engulfed in this bulge, right? And then the number of stars per square, centimeter of the sky is much, much more. And so it just means that there is, the night is beautiful and the night is as bright as the day, right? So that's one interesting bit. And also your sky is going to change, your entire, the constellations that if you like Orion, whatever, those are not there anymore. You have new ideas of, but if your star density is very high, then this whole notion of humans joining dots and making up shapes in the sky would be very different. Maybe we can't be done anymore because there are so many stars in the sky. Then you look at shapes the stars make, and you can think about this. There's a lot of science fiction take place in different planets which are around different stars, and so the stars play an important role in any planet's geometry. It's just we are so far away from the center of the galaxy that our sky at night doesn't have as many stars as could have had. Now you can think about the other aspect of it too. What if we are now here? We are actually in a spiral arm, and in that spiral arm, there's a high density of stars. So we could have been at the same distance from the center of the galaxy, but in between two spiral arms around here, then also the density of stars would be less. And then it's interesting to imagine what will happen if the sun was here. Then the disk through which we see is much smaller, and the density of stars is much less. And so you look up at the night sky, and even when the moon is not there, you don't see so many stars. It's a very, very dark night. And so our whole idea of our mythology involving stars, all those stories we have about stars, would be very different, right? It's very important where we are in our galaxy. And of course, we have gone around the galaxy along with our sun 20 times in our history. History meaning the history of the Earth, which is 4.5 billion years old. In that 4.5 billion years, the sun along with the Earth has gone around 20 times. And so at different times, and humans have only been here for 100,000 years, so we don't know much of that history. But if, for example, we were in a different time in the Earth's history, we would have seen the sky completely differently, right? So your question is much more pertinent than you think. And Mike Vaya, who used to be a professor at GIFR and is a great popularizer, wrote a series of papers along with his students, very, very interesting papers on, as the sun went through our galaxy with the Earth, what did the sun see? What did the Earth see, even though they were not humans?
Very interesting.
And so very, very interesting set of papers that you can figure out, and he's also given talks on this. Anyway, that's a fascinating question, and it's a very fascinating idea to ponder.
Thank you. So it's coming back. Yes. So that's a great way to look at our place in the galaxy and realize that okay, fine, we are still lucky even if we are at the corner. It's not always good to be at the center of attention. And probably there's also a black hole in the story somewhere which could have affected us. But we'll not go into black holes because that leads to various other discussions. But, we have very little time, so I'll take one more really relevant question that which is about galaxies again. So, if is there a center to the universe? That's what Nakul Patil has asked. And the related question is why, if all the galaxies are moving away from each other, why do we see collisions of galaxies? Why is Andromeda going to collide with the Milky Way at some point of time? You're on mute.
Both very, very interesting questions. You asked the collision question is fascinating. What was the first question again, Samir?
Is there a center to the
Yeah.
universe from where everything is moving away?
So that is interesting. So let's look at that first. You have think about the universe is expanding, and what Hubble found was that every galaxy is moving away from every other galaxy, almost. And I'll come to that. That's the second question. We'll come to that in a second. So imagine all galaxies are moving away from each other. And this is, we now know, and of course Hubble did not know that, but soon it became apparent when people like Einstein and Einstein went and met Hubble in the 1930s when he heard that Hubble had made the discovery that everything is moving away. And people like Lemaitre or George Gamow or people like that who were working on the solutions of Einstein's equations to figure out what it actually means. Why is this happening like this? And it turns out that space itself, which Einstein in his theory of relativity called space-time, is the fabric of the universe, and that itself is expanding. And so the space between galaxies is expanding, and the galaxy is just going with the flow to some extent. It's just not stuck in there, but more or less stuck in there. And the space itself is expanding. And as the space expands, galaxies are moving away from each other. Now, then Lemaitre, who was the person who, Father Lemaitre, who was a mathematician who solved Einstein's equations to show this, also asked the interesting question that comes from that, and that is what happens if you take that and if you reverse time, as if you're rewinding the movie, and you go backwards, what happens? So it means that all the things that are moving away from each other will also come closer and closer and closer and closer and closer if time goes backwards, or you are considering time going back. And so at the beginning, all the points that you see in the universe will go to one point. They will all map onto one point. And that's where the universe started from. And that's what Lemaitre called the cosmic egg. But forget about the egg, that confuses you. But it all started from a very small place. So that's the center of the universe. There is no center of the universe. Why? It is the center of the universe, and it is also, there is no center of the universe. Why? Because everybody in the universe maps to that point at t equals 0. Which means that where you are sitting, right, is the center of the universe. Where Andromeda Galaxy is the center of the universe. Where the Virgo cluster is also the center of the universe, because they all go to that point at t equals 0. Everybody came out of that point. So somebody in America, somebody in Australia, and somebody here, they all will go back to the same point if you consider their histories back in time. So every point in the universe is the center of the universe, which means that there is a center of the universe, but it's not really the center of the universe, because the universe is its center. So it's very interesting because of how we understand this expansion. So that's the first question. The second question is also fascinating because the galaxies are not tied to their place in this expanding fabric of the universe space-time. Galaxies are free to move. And galaxies, why would a galaxy move? This is what I dealt with in this talk, so it is a very relevant question. Galaxies are free to move because of gravitation. So a galaxy and another galaxy can only attract each other through the force of gravitation, because on those large scales, no other force, the nuclear force, electromagnetic force, those things are not important. Those are short-range forces. So now, as the universe expands and galaxies are formed in different places, these galaxies have mass and they are attracting each other. So on top of the expansion of the universe, locally, the galaxies that are, and remember, the force of gravity is proportional to the mass, but is inversely proportional to the square of the distance. So very far away things don't pull each other as much with as much force as things that are very close. So we are being pulled by only galaxies um, that are very close to each other. And the force that are on us due to something that's very far away is not as much. So the net motion that we have is a sum of the force, the motion due to the force of the expansion of the universe, and the one that's due to the nearest galaxy pulling us, or nearest galaxies pulling us. And if, for example, we have a nearby galaxy like the Andromeda galaxy, which is pulling us with a force, gmm over r squared, this force that is larger than the force due to the expansion of the universe, then what we would find is that we will fall towards another galaxy. So Andromeda and our galaxy are falling towards each other, right? Whereas nearer local group galaxies are falling towards us, because the force that we are pulling each other with is more than, over that distance, the expansion force of the universe. Does that make sense?
Of course.
Great. Samir, give me 10 seconds. I'm going to come back in a minute.
Sure. All right. So we just wait for a quick thing. So we are through with the questions mostly, because we have very limited time during this interaction. But you are welcome to send us your queries. We have our Facebook page, we have our Twitter handle as well. So you could just tag us and send some questions there if you want. Or you could email us at scipop@gmail.com, scipop, SCIPOP @gmail.com. That's our regular email where you can get more answers to your questions. So with the professor back, we'll ask this last question, and it's relevant to all the students who are attending this talk today, young children, and I also see there must be a lot of parents and also college-going youth. So the question is, what are the prospects of actually doing some work in astrophysics by yourself and making discoveries like you do?
What's the use, you mean?
What's the prospect? I mean, as in, how can they do it themselves?
No, both are important questions. One is what's the use, and one is what you can do with it in life.
Right.
So let us, and both are connected. I mean, you have to figure out what you want from life, right? If you want to make money, then probably astrophysics is not the best way to go. There are very rich astrophysicists I know. For example, I used to know Sterling Colgate, who worked out how stars become supernova. The supernova, so many papers by Colgate, and he was the heir of the Colgate family, one of the richest people in the world. He used to come to conferences in his own private yacht and things like that. So there are some very rich astronomers, but they didn't make money in astronomy. So, and a lot of people think about careers as ways of where they will earn a lot of money. But I'm sure you are not one of them, because you're listening to my talk here, and we are in this discussion, and you have some curiosity about physics and astronomy and subjects like that. And if you look at the other end of the spectrum, you will see that you would probably long term want to do something in life which you will like doing, right? And so this is what we do. In the middle of the night, I wake up and think, why am I sleeping? I'd rather go and do some work. In the morning, I get up and I can barely brush my teeth because I really want to get on my desk and start doing my work. And this I've done, I'm almost at the end of my career, and I still want to do this work. You want to know whether you want to do a job which you like this much, or you want to be in a job where from Tuesday you're thinking, when will Saturday come? And I'll get, when will Sunday come, right? Even though you are getting a salary and you want a lot of money. So one of the important things is you have to figure out what you're happy with. What kind of career you want. It's wonderful to do something for 1 or 2 years, 3 years, but if the entire life if you want to do something, make sure you choose something that you like doing. Okay, so that's my human aspect of it. More operationally, if you made a choice that you want to do physics and astrophysics research, then let me tell you that astrophysics is a subject which welcomes people from many backgrounds, because in order to do astrophysics, we need expertise from many different subjects. For example, I did physics, and a lot of people come from physics. But within physics also, we need people who know a lot about atomic physics, nuclear physics, electronics, because you have to build the instruments. You want to know about lasers, you want to know about optics, you want to know about condensed matter physics or solid state physics, because again, that is important in the materials that we use to build detectors, all kinds of things. Then we want engineers, because we have to build these things, and also engineers have these expertise. So civil engineers, computer engineers, chemical engineers, electronics engineers, electrical engineers are full. I mean, 2 days ago we had a talk by Niku Madhusudan, who is a professor of extrasolar planets in Cambridge University, who's one of the most famous astronomers in the world now, and he did his mechanical engineering from BHU IIT, right? So we have on my faculty here lots of people who have studied engineering and come to do work in astronomy, astrophysics. So you can do engineering, you can do chemistry, you can do mathematics, you can do statistics, you can do physics, but you have to do a very good undergraduate degree, because astronomy in our country at least is not an undergraduate degree yet. If you were in Europe or in America, you could have done astronomy, astrophysics at an undergraduate level. But in order to, I don't think that is a very good thing also, because astronomy requires a very strong undergraduate degree in one of these subjects I talked about. And once you do that, then what you do is you start doing some research. You can do some research in astronomy, astrophysics in your master's degree. And already in this country, there are quite a few master's programs in astronomy, astrophysics. From this year, later this year, IUCAA is going to start a master's program with Pune University on astronomy, astrophysics. Look out for it. There will be announcements for it. And IIT Indore has master's programs. St. Xavier's College in Mumbai has a master's program in astrophysics. There are many other master's programs. And then there are physics and associated subjects which have astronomy, astrophysics, and a master's program. Even if you don't have astrophysics in your master's programs, you can start doing a PhD. And for that, you have to, for master's programs as well, you have to sit for national exams, and one of them is JEST. The JEST exam is an entrance exam for PhD programs in lots of different kinds of physics all over the country. And then there are other PhD admission programs. IUCAA has its own called INAT. And other institutions in India have similar programs. The Raman Institute, the Indian Institute of Science has the Joint Astronomy Program, JAP, which you can join after a master's or a BTech. And then the Tata Institute's radio astronomy branch here in NCRA, all of these places. And you can start a PhD. And I think to become a professional astronomer, you need a PhD. But long before that, while you're doing your master's or your bachelor's program, you can start doing small bits of research with somebody at the different institutions or institutes as well as universities who do astronomy. And so we can provide you with advice on this, but also on the web, you can find quite a lot of this.
Thank you so much. That was, I think, the very good information for all the prospective students, astrophysics students of the future. But anyway, you can also continue it as a hobby in case you're not really a student level person, if you're a parent or you have very little kids, you can get them interested in astronomy. This is a fascinating subject and a lot to do, as the professor has said. You could use small telescopes like I have in the back here, and do your own observations. That will get you into the habit of doing something yourself. Thank you. This has been a lovely interaction, and we got to know a little bit more about our place in space from an astronomer and astrophysicist who actually researches on galaxies, which are these really fascinating things up in the sky, very faint, very far away, but have so much in them to discover. So with this, I thank everyone for being here, and I also thank Professor Somak Raychaudhury for his time. We will continue this series. We'll be doing some surveys about whether we should continue throughout the vacation. We will be very happy to do that, and we'll get back to you. Keep following our social media handles, and also subscribe to our channels if you want to get update about any other programs which happen live or are premiered on this channel. So do that, and we'll see you at the next interaction. Take care, and these are very difficult times. All of you should stay at home and stay safe. So do that, and we'll see you back in the next event. Thank you very much.
Thank you. Bye. Thank you, Samit. Thanks everybody for coming.